Hello students, we are starting our first lecture, Introduction to Molecular Spectroscopy. Scientists in all fields are deeply interested in knowing the structures of molecules. Our knowledge about molecular structure is derived indirectly from the technique known as spectroscopy, which deals with the interaction of radiation with matter. In this first lecture, we will discuss the nature of electromagnetic radiation and the sort of interactions which may occur by radiations. You all know that at all time we are all being showered by electromagnetic waves. Electromagnetic waves are interconnected electric and magnetic fields that are perpendicular to each other. In this picture, you can see an electromagnetic wave. Its electric field traveling in the XY direction and the magnetic field perpendicular to the electric field in the XZ direction. We have different properties to characterize a wave. One wave includes a crest and a trough, and it can be considered as one wavelength, or by usual definition, it is the distance between two crests or troughs. A wave has an amplitude also, which is the displacement of wave from the rest position. It is calculated by the distance between the crest and the rest position, or the trough and the rest position. In spectroscopy, wavelengths are expressed in a variety of units: millimeter, centimeter, micrometer, nanometer, angstrom, etc., depending on the region from which the wave propagates. Another property of a wave is the frequency, which is the number of waves that pass through a fixed point at a given time. You can see two waves traveling at same speed. One has a shorter wavelength and the other has a longer wavelength. More peaks of shorter wavelength wave will pass by you in a given time. For shorter wavelength wave, the number of peaks passing is higher, that is, it has the higher frequency. For keeping a constant speed of light, the wave has to change its characteristics of frequency or wavelength, where c is the velocity of light. From this equation, the frequency can be expressed as c by lambda, and its unit is hertz. There is a third way by which a wave can be characterized, and this is the wave number nu bar, which is the reciprocal of wavelength, and it is expressed in centimeter inverse. By Planck's quantum theory of radiation, the energy of an oscillator is discontinuous, and any change in its energy content can occur by means of a jump between two distinct energy states. Here I am giving a simple hydrogen-like atom containing one electron. For this, the energy difference between the two levels E1 and E2 is delta E, which is equal to h nu by Planck's approximation. That is, a radiation of frequency nu having h nu energy would be needed for the electron to excite from E1 to E2, or an energy h nu will be emitted by the de-excitation of electron from E2 to E1. The first transition leads to absorption spectrum and the second leads to emission spectrum. In contrast to atomic spectra, which arises from the transition of an electron between atomic energy levels, the molecular spectra arises by different types of transitions. Let us illustrate these transitions with reference to a diatomic molecule. A molecule possesses different kinds of energy for its different mode of movements. First is the translational energy. By the result of translational motion, this is a random motion of the molecule as such, and during this motion the center of gravity of the molecule changes. The rotational energy arises when the molecule rotates about an axis perpendicular to the internuclear axis and passing through the center of gravity of the molecule. Vibrational energy is associated with the to and fro motion of the molecule such that the center of gravity does not change. And finally, the electronic energy is associated with transition of an electron from one level to another by absorption or emission of radiation. Thus, for a molecule, the energy absorbed by radiation can be utilized to translate, rotate, vibrate, or exciting the electron. Hence, the total energy of a molecule can be written as the sum of nuclear energy, translational energy, rotational energy, vibrational energy, and the electronic energy. As it is more accurate to measure the change in energy other than the energy at a specific position, we can have change in the total energy equal to the sum of change in these separate energies. According to Born-Oppenheimer approximation, the nucleus is assumed to be fixed since it is having high mass compared to electron. So, the change in nuclear energy can be avoided. And also, since the translational energy is extremely small and is not quantized, it can be also avoided. So, by Born-Oppenheimer approximation, the total energy change of a molecule arises by the sum of change in rotational energy, change in vibrational energy, and the change in electronic energy. Furthermore, the electronic energy is very much higher than vibrational energy change, which is higher than rotational energy change. We can make it clear by considering a molecular energy level diagram. Here we have two electronic levels, a ground electronic energy level and an excited electronic energy level. Associated with each electronic energy level, there is a series of vibrational energy levels, and associated with each vibrational levels, there will be a series of rotational energy levels. Hence, the molecular spectrum is very much complicated as different transitions may be possible simultaneously. Here, it can be possible to have an electronic transition, a vibrational transition between two different electronic states, or transition within the electronic state, or a rotational transition within the electronic state, etc. For each energy level transition, we need different types of radiation having different energy. There is the importance of electromagnetic spectrum, where the electromagnetic radiations have been divided into various regions such as radio waves, microwaves, infrared waves, visible light, ultraviolet radiations, X-rays and gamma rays. It has been arranged in the increasing order of frequency or decreasing order of wavelength. Each region of spectrum containing waves can give rise to different molecular spectra when the wave enters a molecule. The radio wave, which has the lowest energy, gives nuclear magnetic resonance spectra, which we will discuss in coming classes. The microwave region gives rise to rotational or microwave spectroscopy. That is, this low energy radiation can cause rotational energy transition, energy level transition. Similarly, the infrared radiation can give rise to vibrational spectroscopy or IR spectroscopy. Visible and UV can give rise to electronic spectra, which is given by high energy transition between electronic levels. Again, gamma rays can give Morse-Bohr spectroscopy. In the coming lectures, we will see each spectroscopy in detail. I hope you got an idea about different energies possessed by a molecule and the radiations which causes a change in these energies. Thank you very much.